Well, hello, AP Physics students. Got a problem for you to do. We're talking about center of mass and center of gravity today. So, as it turns out, people have different centers of mass. That's not always exactly halfway in between a person's head and their toes. It might kind of depend on them. For instance, Mr. Kirsten has really, really big arms, giant. You've probably seen him if he's working out on the gym, at the gym. So his center of mass is a little higher. Anyway, so different people have a different center of mass. Most people, it's about right in the middle of them. But here is a problem that asks about figuring out where is the center of mass of a person. So here's the plan. In this problem, we are told, number 19 here, that a person who is 172 meters tall sits on a plank that is very light, meaning you can ignore the mass of the plank. Being physicists, you start to catch on what some of these terms mean. And anyway, the scales read, kind of strange because the scales read in kilograms here. But the scale closest to their feet reads 31.6 kilograms. The one closest to their head, 35.1 kilograms. Where is the center of mass of this person? And in this problem, it actually says, where is it in relation to their feet? So this is a good static equilibrium problem. And let's go ahead and dive in here and see what we know. The first thing we're going to do is let's just draw a good old free body diagram, right? So three forces acting on this setup here. So we got the overall mass of the person that is somewhere in the middle. And we're going to call that position X over here because basically we're solving for X here. So this dot here represents the center of mass of the system or of the person. And so anyway, the person's mass, because of their weight, would be pulling down. Now we also know that these scales on either end are pushing up. And even though those scales are reading in kilograms, we'll put a G next to them since this is a free body diagram. We want all of these to be forces, not masses. All right. So I've got three forces here acting on this system that is in equilibrium. So by now you should have practiced quite a bit that equilibrium means two things. The first thing it means, dun dun dun, the net force must be zero on the system. All right, net force must be zero. Right, the system is at rest and it's staying at rest. Therefore, the net force must be zero. So let's add up all the forces here. A positive 31.5 times G would be the force up there. Got a 31.6 times G force up here. And then a minus mg, or the overall weight of the person down. So that must add up to be zero. So if we just do a little algebra there and cancel out our g's, we can figure out what the mass of our person is here. So it turns out that the mass of our person is about 66.7 kilograms. So if you were to multiply that by about 2.2 pounds near the surface of the Earth, that would be about a 150-pound person or so. A reasonable number there. But Mr. Kirsten, you can't interchange kilograms and pounds. Kilograms is a unit of mass, and pounds is a unit of force. That very true, very true. Point taken. So anyway, we know the mass of the person. That's a good first step. But we still don't know where the center of mass of this person is. So let's, for that, we're going to rely on equilibrium condition number 2. The net torque on the system must be zero. Okay, so I'm going to go ahead and pick this point right here, the rightmost point, as my lever point here. with that being said, this force exerts no torque on the system, right? And then if I go out a distance x, that's the length of my lever arm here is x. I don't know what x is. And then I have the weight down, right? So this weight of the person down would make a torque spinning the system in this direction, right? That is a counterclockwise torque, so we assign that a positive number. And then this torque over here would make the system spin this way. That is a clockwise torque, so we assign that a negative value there. Notice we don't have to use sines or cosines here. Each force is perpendicular to the moment arm, so that means our angle is 90 and sine 90 is 1. So perpendicular, so maximum torque there, so no angles to mess around with there. So once we get to here, once again, those G's will cancel out. Let's see, this M here is equal to so let's see, I did a little rearranging here. I brought this guy to the, so what did I do? I canceled out the G's, right? And then I brought this guy here to the other side of the equation and made it positive, right? So x is what we're solving for there, and dividing by 66.7, I get that this person's center of mass is 0.9 meters away from their feet. So it looks like this person center of mass is a little taller, a little higher than halfway. All right. So yeah. Now I've been kind of using the term center of mass and center of gravity interchangeably. Can I do that? The answer is 99% of the time the answer is yes. What is the center of mass? It just means if you had to take an object and pick one point in the object, that you can assume that object's a point particle and all its mass is concentrated there, that would be the point. And center of gravity is the same thing, except replace the term mass with I'm going to assume all gravity is acting there. When would these two ever be different? The only case these would be different is if you had some weird sort of non-uniform gravitational field. That is, if G was 9.83 at your feet and 9.80 at your head, then your center of gravity and your center of mass would be different. Again, for our purposes, you can almost use these terms interchangeably. I would use the term center of mass just because while this deals just with gravity, this will deal with everything. So center of mass is the term I'd want to use. All right, nice job, physics students, for your joke today. All right, what do you call a snarky criminal going down a set of stairs? A snarky criminal going down a set of stairs? You call that a condescending. Condescending. Oh, Mr. Kirsten, you're going down. All right, nice job, physics students. We'll see you tomorrow.